A star is not eternal, even though it may seem so when we look at the night sky. It burns with a steady light for millions or even billions of years, appearing unchanging from our small perspective on Earth. But every star carries within it a hidden struggle, a long and delicate balance between two opposing forces. On one side is gravity, constantly pulling everything inward, trying to compress the star into the smallest possible volume. On the other side is nuclear fusion, the process happening in the star's core that releases enormous energy and pushes outward against that collapse. As long as these two forces remain in balance, the star survives. But this balance cannot last forever. Deep inside a star, matter is under extreme pressure and temperature. Hydrogen atoms are forced together so violently that they fuse into helium, releasing energy in the process. This energy does not travel outward instantly, but over long periods it moves through the star, eventually reaching the surface and escaping as light and heat. This is what we see when we look at a star in the night sky. It is not just glowing matter. It is a controlled nuclear reaction, sustained by the delicate equilibrium between inward pressure and outward energy release. For most of a star's life, this equilibrium holds steady. Gravity tries to compress the star, but fusion provides enough pressure to resist that collapse. The star is stable, and this stability can last for a very long time. But stability does not mean permanence. The fuel that powers fusion is not infinite. Hydrogen, the simplest and most abundant element in the universe, slowly becomes depleted in the star's core. As this happens, the internal structure of the star begins to change. When hydrogen runs low, the star begins to fuse helium instead. This process requires even higher temperatures and pressures, so the core contracts further under gravity. As it contracts, it heats up, allowing new fusion reactions to begin. The star enters a new phase of its life, often expanding into a much larger and more luminous object. In this stage, it may become a red giant or a supergiant, depending on its initial mass. The outer layers expand while the core continues to evolve, building heavier and heavier elements through successive stages of fusion. Each stage of fusion produces less energy than the one before it, and each requires higher temperatures to sustain. The star is gradually climbing a ladder of nuclear reactions, forging elements like carbon, oxygen, neon, and silicon. But this process has a limit. Iron represents a critical turning point. Unlike lighter elements, iron does not release energy when fused. Instead, it absorbs energy. This means that once a star begins to produce iron in its core, the process that has sustained it for millions of years begins to fail. At this stage, the core of the star is layered like an onion. Heavier elements form in the center, surrounded by shells of lighter fusion reactions. Iron accumulates in the very core, growing larger over time. But unlike earlier stages, there is no energy source to support this iron core. It does not generate outward pressure. It simply sits there, growing in mass as more material is added from above. Eventually, the iron core reaches a critical mass. Gravity becomes too strong for any remaining pressure to resist. the core can no longer support itself. In a fraction of a second, everything changes. The collapse begins. This collapse is not gradual. It is incredibly fast, happening in less time than it takes for light to cross a city. The core of the star, once stable and supported by nuclear reactions, suddenly loses its ability to resist gravity. It begins to fall inward at a significant fraction of the speed of light. Matter is crushed together so intensely that atomic structures are destroyed. Electrons are forced into protons, forming neutrons and releasing a flood of neutrinos, nearly massless particles that carry energy away from the collapsing core. As the core collapses, the outer layers of the star do not immediately follow. They are still supported by the pressure generated from the previous fusion processes. But the collapse of the core creates a void, a sudden drop in internal support. The outer layers begin to fall inward as well, accelerating under the pull of gravity. At the center, something extraordinary happens. The collapsing core reaches a point where neutrons themselves resist further compression. This creates an incredibly dense object known as a neutron star. In some cases, if the mass is too great, even neutron pressure cannot stop the collapse, and the core continues inward to form a black hole. But in many cases, the core stabilizes as a neutron star, only a few kilometers in diameter, but containing more mass than the Sunday. The formation of this dense core marks a dramatic change in the behavior of the surrounding star. The infalling outer layers meet the resistance of the newly formed neutron core. The collision generates an enormous amount of energy, creating a shockwave that travels outward through the star. This shockwave is the beginning of the supernova explosion. For a brief moment, the energy released in this process exceeds the combined light of entire galaxies. The outer layers of the star are violently ejected into space at enormous speeds. The star is torn apart in one of the most energetic events in the universe. What was once a stable, shining object becomes a rapidly expanding cloud of gas and debris. This explosion is not just a destruction, it is a transformation. The material that made up the star is not lost, it is thrown into space, carrying with it the elements that were forged in the star's core. Carbon, oxygen, silicon, and many heavier elements are scattered across the cosmos. These materials will later become part of new stars, planets, and eventually life itself. The energy released during a supernova is so vast that it briefly outshines everything else in its galaxy. From vast distances, it appears as a new point of light in the sky, sometimes visible even in daylight. Ancient observers recorded these sudden appearances, not knowing they were witnessing the death of a star. But the visible light is only part of the story. Most of the energy from a supernova is carried away by neutrinos, which pass through matter almost completely unaffected. These particles stream out from the collapsing core in an enormous burst, carrying away information about the conditions at the very heart of the explosion. The shock wave produced by the explosion continues to expand long after the initial event. It sweeps through surrounding space, compressing gas clouds and triggering the formation of new stars. In this way, the death of one star becomes the birth of many others. The universe recycles its material in a continuous cycle of destruction and creation. As the remnants of the explosion expand, they form structures known as supernova remnants. These glowing clouds of gas can persist for thousands of years, gradually mixing with the surrounding interstellar medium. Over time, they lose their brightness, but their influence remains. They enrich the galaxy with heavy elements and shape the conditions for future generations of stars. Inside these remnants, complex processes continue. Shockwaves heat the gas, magnetic fields are amplified, and particles are accelerated to near light speed. These environments become natural laboratories for high-energy physics, revealing conditions that cannot be recreated on Earth. The death of a star is not an isolated event. It is part of a larger cosmic cycle. Stars form from clouds of gas, live for millions or billions of years, and then return their material to space through supernova explosions. This cycle repeats over and over, gradually enriching the universe with the elements needed for more complex structures. Without supernovas, the universe would be a very different place. It would be filled mostly with hydrogen and helium, the simplest elements. There would be no carbon for life, no oxygen for water, no iron for planets. The explosive death of stars is what makes chemical complexity possible. As we look deeper into the nature of these events, we begin to see that they are not just endings, they are transitions. They represent the moment when a star stops being a stable source of energy and becomes a catalyst for change on a galactic scale. In the quiet aftermath of a supernova, the universe carries forward the legacy of the star that once was. Its matter spreads across space, its energy shapes new structures, and its remnants continue to influence the evolution of galaxies. And in this cycle of collapse and rebirth, we find one of the most fundamental processes shaping the cosmos. Every star lives a life defined by balance. It is a constant struggle between inward and outward forces, between collapse and expansion, between gravity pulling everything toward the center and nuclear reactions pushing outward from within. This balance is not accidental. It is the reason stars can exist at all. Without it, every star would either collapse instantly into a dense point or disperse into space. Instead, they shine steadily for millions or billions of years, holding themselves together through a delicate equilibrium that slowly shifts over time. At the heart of this balance is nuclear fusion. In the core of a star, temperatures reach millions of degrees, and pressures are so extreme that atoms are forced to collide and merge. Hydrogen nuclei combine to form helium, releasing enormous amounts of energy in the process. This energy travels outward, creating pressure that pushes against gravity. It is this outward pressure that prevents the star from collapsing under its own weight. Gravity, however, never stops working. It is constantly pulling every particle of the star inward, trying to compress it into the smallest possible space. The more massive the star, the stronger this inward pull becomes. For most of a star's life, these two forces remain in balance. The outward pressure from fusion matches the inward pull of gravity, and the star remains stable. But this balance is not permanent. It depends entirely on the availability of nuclear fuel. As long as hydrogen is present in the core, fusion continues. Over time, however, hydrogen becomes depleted. The core begins to change. It contracts under gravity, becoming hotter and denser. This contraction allows new fusion processes to begin in surrounding layers where hydrogen is still available. As the core shrinks, the outer layers of the star respond dramatically. They expand outward, sometimes growing hundreds of times larger than the original size. The star becomes a giant, luminous object, often red in color due to its cooler surface temperature. Despite this expansion, the core continues to evolve, quietly burning through successive stages of fusion. Helium becomes the next fuel source. Under even higher temperatures, helium nuclei fuse to form heavier elements like carbon and oxygen. This process releases energy, but not as efficiently as hydrogen fusion. The star must contract further to maintain the necessary conditions. Each new stage of fusion requires greater pressure and temperature, pushing the star closer to the limits of what it can sustain. This sequence continues in massive stars, which are able to reach the extreme conditions needed to fuse progressively heavier elements. Carbon, neon, oxygen, and silicon are all produced in successive layers deep within the star. Each layer surrounds the core like an onion, with different elements burning in different shells. The structure becomes increasingly complex as the star ages. But there is a limit to this process. Fusion can only produce energy up to a certain point in the periodic table. Iron marks that boundary. Unlike lighter elements, iron does not release energy when fused. Instead, it consumes energy. This means that once iron begins to accumulate in the core, the star's ability to sustain itself begins to collapse. The iron core grows silently, layer by layer, as fusion continues in surrounding shells. But the core itself is inert. It does not generate outward pressure. It simply becomes heavier and more compressed. Eventually, it reaches a critical point where even the forces supporting it can no longer hold it up. At this moment, the balance that has sustained the star for its entire life breaks down. Gravity wins, the core begins to collapse. This collapse is not gradual, it is catastrophic. In less than a second, the core shrinks dramatically, compressing matter to densities far beyond anything found under normal conditions. Electrons are forced into protons, forming neutrons and releasing an enormous burst of neutrinos. These nearly massless particles carry away a significant portion of the energy from the collapse, streaming outward in all directions. While the core collapses inward, the outer layers of the star are still falling toward the center, but something changes when they encounter the rebounding core. The collapse halts abruptly as neutron degeneracy pressure, a quantum mechanical effect, resists further compression. The core becomes incredibly dense, forming either a neutron star or, if the mass is large enough, continuing on to become a black hole. The sudden halt of the core's collapse sends a powerful shockwave outward. This shockwave travels through the infalling outer layers, reversing their direction and ejecting them into space. The result is a supernova explosion, one of the most energetic events in the universe. In a matter of seconds, the star is transformed. What was once a stable, shining object becomes a rapidly expanding cloud of gas and debris. The energy released is so immense that it can briefly outshine entire galaxies. From vast distances, a supernova appears as a sudden new point of light in the sky, marking the dramatic end of a star's life. But this end is also a beginning. The material that made up the star is not destroyed. It is scattered into space, enriched with heavy elements formed during the star's lifetime. These elements include carbon, oxygen, silicon, and many others essential for the formation of planets and life. In this way, supernovas play a crucial role in the chemical evolution of the universe. The shockwave from the explosion does more than disperse material. It also interacts with surrounding gas clouds, compressing them and triggering the formation of new stars. Regions that were once diffuse and inactive are suddenly energized, collapsing under gravity to form new stellar systems. The death of one star becomes the catalyst for the birth of many others. As the supernova remnant expands, it forms a complex structure of glowing gas and shock fronts. These remnants can persist for thousands of years, gradually blending into the interstellar medium. Over time, they lose their brightness, but their influence remains embedded in the surrounding environment. Inside these expanding remnants, physical conditions are extreme. Temperatures are high, magnetic fields are strong, and particles are accelerated to near light speed. These environments serve as natural laboratories for high-energy physics, allowing scientists to study processes that cannot be replicated on Earth. One of the most important consequences of supernovas is the enrichment of the universe with heavy elements. Without these explosions, the cosmos would be dominated by hydrogen and helium, the simplest elements formed in the early universe. Supernovas create the diversity of elements necessary for planets, chemistry, and life itself. Every atom of iron in blood, every atom of calcium in bones, every atom of gold in jewelry was forged in the core of a star and scattered by a supernova explosion. The cycle of stellar evolution does not end with a single explosion. It continues across generations of stars. Material ejected by one supernova becomes part of the next generation of stars and planets. Over billions of years, this recycling process gradually increases the complexity of the universe. Massive stars play a particularly important role in this cycle. Their short but intense lives end in supernova explosions that dramatically reshape their surroundings. They influence the structure of galaxies, regulate star formation, and drive the flow of matter through cosmic environments. Even the remnants left behind by supernovas continue to shape the universe. Neutron stars, with their extreme density and powerful magnetic fields, represent some of the most exotic objects known. Black holes, formed when the collapsing core is too massive to stabilize, create regions where space-time is warped to its limits. Through all of this, the balance between gravity and nuclear energy remains central. It governs the life of a star, determines the nature of its death, and influences the structure of the universe on the largest scales. When that balance fails, the result is not simply destruction, but transformation on a cosmic scale. Supernovas are not rare accidents. They are essential events in the life cycle of galaxies. They distribute matter, shape structure, and drive evolution across the cosmos. Without them, the universe would remain chemically simple and structurally uniform. With them, it becomes rich, diverse, and capable of forming complex systems. As we observe these explosions, we are witnessing not just the end of a star, but the continuation of a process that connects everything in the universe. Each supernova is a reminder that even in destruction there is creation, and even in collapse there is the beginning of something new. When a massive star reaches the end of its life, the most violent transformation in the universe begins deep within its core. At first, nothing on the surface seems to change. The star still shines, still burns, still holds its familiar shape in the sky, but inside, the structure is becoming unstable. Layers of nuclear burning are stacked like fragile shells, each one dependent on the one beneath it. And at the very center, an iron core is quietly growing, no longer producing energy, only consuming it. This core is the beginning of the collapse that will eventually lead to a supernova. Iron is a turning point in stellar evolution. Up to this stage, fusion has been a source of power. Hydrogen becomes helium, helium becomes carbon, carbon becomes heavier elements, and each step releases energy that pushes outward against gravity. But iron breaks this pattern. When iron is fused, it does not release energy, it absorbs it. This means that once a star builds an iron core, it is no longer supported by nuclear energy. The core becomes a dead weight at the center of a living system. As more iron accumulates, the core grows heavier and more compressed. Gravity continues to act without opposition. The core becomes so dense that electrons are forced into a state where they can no longer resist being squeezed together with protons. At this point, a process known as electron capture begins. Electrons merge with protons to form neutrons, releasing a flood of neutrinos in the process. These neutrinos are nearly massless and interact very weakly with matter, allowing them to escape the core almost instantly, carrying away vast amounts of energy. This loss of pressure support triggers the collapse. The core is no longer stable. It begins to fall inward under its own gravity. But this is not a slow process. It is a catastrophic implosion that happens in a fraction of a second. The core shrinks dramatically, compressing matter to densities that cannot exist under normal conditions. Atoms lose their structure entirely. Electrons are stripped away. Nuclei are crushed together. The core becomes a sea of neutrons, packed so tightly that a single teaspoon of this material would weigh billions of tons. As the core collapses, the outer layers of the star are still suspended above it. For a brief moment, they are unaware of what is happening below. They continue to fall inward under gravity, drawn toward the collapsing center. But something extraordinary is about to happen that will reverse this motion completely. When the core reaches a certain density, a new force comes into play. Neutron degeneracy pressure resists further compression. This is not a force in the traditional sense, but a consequence of quantum mechanics. Neutrons, like electrons, obey the rules of quantum exclusion, which prevent them from occupying the same state in the same space. When matter is compressed to extreme densities, this quantum resistance becomes powerful enough to halt the collapse. At this point, the core abruptly stiffens. The inward motion stops and rebounds. This rebound sends a powerful shockwave outward through the infalling material above. The shockwave is not just a simple push, it is a massive transfer of energy that transforms the entire structure of the star in an instant. The outer layers, which were collapsing inward, are suddenly struck by this outward moving shock. The change is so rapid that the material is violently ejected into space. The star is torn apart from the inside out. What was once a stable structure becomes a rapidly expanding cloud of gas and debris moving at enormous speeds. This is the moment of the supernova explosion. It is one of the most energetic events in the universe, releasing more energy in a few seconds than the Sun will emit in its entire lifetime. For a brief period, the explosion can outshine an entire galaxy, visible across vast cosmic distances. But the explosion is not just a release of energy, it is a transformation of matter. The outer layers of the star are not destroyed. They are scattered into space, carrying with them the elements that were forged inside the star over millions of years. Carbon, oxygen, silicon, sulfur, and many heavier elements are all expelled into the surrounding environment. Inside the core, the outcome depends on the original mass of the star. If the core is below a certain threshold, it stabilizes as a neutron star. This object is incredibly dense and compact, with a diameter of only a few kilometers, but a mass greater than that of the Sunday. If the core exceeds this threshold, gravity overwhelms even neutron degeneracy pressure, and the collapse continues unchecked, forming a black hole. The shockwave that drives the explosion moves outward through the star at tremendous speed. It encounters layers of material that were built up over the star's lifetime. Each layer reacts differently depending on its composition and density. Some regions are compressed and heated, triggering additional nuclear reactions that produce even heavier elements. Others are simply torn apart and accelerated outward into space. As the shockwave reaches the surface of the star, the explosion becomes visible. Light is suddenly released in a burst of radiation that travels across the universe. This light carries information about the energy of the explosion, the composition of the star, and the processes occurring deep within the core. It is one of the primary ways astronomers study supernovas, allowing them to reconstruct events that happened in distant galaxies millions or even billions of years ago. However, the visible light is only a small fraction of the total energy released. The vast majority is carried away by neutrinos. These particles are produced in enormous numbers during the collapse of the core and pass through matter almost without interaction. They stream out of the star in a burst that lasts only seconds but carries away a significant portion of the energy of the explosion. The detection of neutrinos from a supernova provides a unique window into the core collapse process. Unlike light, which can be delayed or altered by the outer layers of the star, neutrinos escape directly from the core. They offer a glimpse into the earliest moments of the explosion, revealing conditions that cannot be observed in any other way. After the explosion, the remnants of the star continue to expand into space. This expanding cloud of gas is known as a supernova remnant. It consists of material from the star mixed with surrounding interstellar gas. Over time, this remnant grows larger and more diffuse, eventually blending into the galaxy. Within the remnant, shockwaves continue to propagate through the gas. These shocks heat the material to extreme temperatures and generate strong magnetic fields. Particles within the remnant are accelerated to near light speed, creating cosmic rays that travel through the galaxy and beyond. These high-energy particles play an important role in shaping the environment of space. The expanding material also interacts with nearby gas clouds. The pressure and energy from the explosion can compress these clouds, triggering the formation of new stars. In this way, supernovas not only destroy, but also create. They scatter the elements needed for future generations of stars and planets, while also initiating the processes that lead to their formation. Over time, the chemical composition of the galaxy changes. Each generation of stars enriches the interstellar medium with heavier elements. These elements accumulate over billions of years, gradually increasing the complexity of matter available for new structures. Without supernovas, the universe would remain simple and chemically limited. With them, it becomes diverse and capable of forming complex systems. The remnants of supernovas can persist for tens of thousands of years. During this time, they evolve in shape and structure, influenced by magnetic fields, surrounding gas, and the motion of the galaxy itself. Eventually, they fade into the background, leaving behind only subtle traces of their existence. But the impact of a supernova does not end with its visible remnants. The elements it disperses become part of new stars, planets, and even living organisms. The calcium in bones, the iron in blood, the oxygen in air, and the carbon in all organic molecules were all forged in ancient stars and distributed by supernova explosions. In this sense, every atom in the universe carries a history written in stellar death. The core collapse that initiates a supernova is one of the most extreme events in nature. It compresses matter to densities that challenge our understanding of physics and pushes space and time to their limits. It reveals the interplay between quantum mechanics and gravity, between microscopic particles and cosmic scale forces. Each supernova is both an ending and a beginning. It marks the death of a star, but also the creation of new possibilities. It reshapes galaxies, drives chemical evolution, and seeds the universe with the ingredients for future complexity. In the silent aftermath of the explosion, the universe continues its long process of change. The remnants expand, the elements disperse, and new stars begin to form. And somewhere in this ongoing cycle, the story of matter, energy, and space continues to unfold. After the violent collapse of a massive star and the explosive release of a supernova, the universe does not fall into silence. Instead, it becomes more active in new and unexpected ways. The shockwave from the explosion travels outward through space, carrying energy, matter, and the seeds of transformation. It does not simply dissipate into nothing, it reshapes everything it touches. What follows a supernova is not emptiness, but a period of cosmic restructuring, where new stars, new systems, and even new worlds begin to take shape. The first thing to understand is that space between stars is not truly empty. It is filled with gas, dust, magnetic fields, and low-density plasma. This material is often spread out over vast regions, forming clouds that are invisible to the naked eye. These interstellar clouds are the raw material for star formation. They are quiet, cold, and diffuse, existing in a delicate balance between gravity and internal pressure. On their own, they may remain stable for millions of years without significant change. When a supernova occurs nearby, This balance is disrupted. The explosion sends a powerful shockwave racing through space. This wave is not like sound in air, but a vast compression front moving through interstellar material. As it passes through a gas cloud, it compresses the material, increasing its density and temperature. Regions that were once too diffuse to collapse under gravity are suddenly pushed past a critical threshold. This compression is the first step in a process that leads to the birth of new stars. As the shock wave moves through a cloud, it creates ripples of density. Some regions become slightly denser than others. These small differences are enough for gravity to take over. Once a region becomes dense enough, it begins to pull in more material from its surroundings. The process accelerates, and a collapsing core begins to form. This is the beginning of star formation, triggered by the death of another star. It is a cycle where destruction becomes the catalyst for creation. The energy released by a supernova does not simply disperse, it organizes matter in new ways, setting the stage for the next generation of stars. As the collapsing regions within a gas cloud grow denser, they begin to heat up. Gravity pulls material inward, converting potential energy into thermal energy. The core of the collapsing region becomes hotter and hotter, eventually reaching temperatures high enough to ignite nuclear fusion. At this point, a new star is born. Surrounding this forming star is often a rotating disk of gas and dust. This disk is a natural consequence of conservation of angular momentum. As material falls inward, any slight rotation becomes amplified. The disk flattens and spreads out, creating a structure where planets can eventually form. Within this disk, dust grains collide and stick together, gradually building larger and larger bodies. Over time, these particles grow into planetesimals, then into protoplanets, and eventually into fully formed planets. The composition of these planets depends on the materials available in the disk. Heavier elements produced by previous generations of stars, especially those dispersed by supernovas, play a crucial role. Without these elements, rocky planets like Earth could not exist. In this way, supernovas directly contribute to the formation of planetary systems. They enrich the interstellar medium with the elements needed for complex chemistry. They provide the building blocks for solid surfaces, atmospheres, and eventually the conditions necessary for life. The shockwave from a supernova does not affect only one region. It spreads outward in all directions, interacting with multiple clouds and structures within a galaxy. This means that a single supernova can influence star formation across vast regions of space. In some cases, it can trigger the birth of entire clusters of stars, creating groups of stellar systems that form together from the same event. These star clusters often remain loosely bound by gravity for some time before dispersing. Within them, stars of different masses evolve at different rates. Massive stars burn quickly and end their lives in supernova explosions, while smaller stars continue to shine for billions of years. This creates a dynamic environment where cycles of death and birth overlap continuously. As new stars form, they inherit the chemical history of the universe. Each generation contains more heavy elements than the one before it. This gradual enrichment changes the nature of matter itself. Early stars were composed almost entirely of hydrogen and helium. Later stars contain a wide variety of elements, allowing for more complex planetary systems and chemistry. The role of supernovas in this chemical evolution cannot be overstated. They are the primary mechanism by which heavy elements are distributed throughout galaxies. Elements such as carbon, oxygen, silicon, and iron are all produced in the cores of massive stars and released during their explosive deaths. Without this process, the universe would remain chemically simple and incapable of supporting the complexity we observe today. Supernova shockwaves also shape the structure of galaxies themselves. As they move through the interstellar medium, they carve out cavities and compress surrounding gas into shells and filaments. Over time, these structures influence the overall distribution of matter within a galaxy. Regions of active star formation often appear along the edges of these compressed structures, creating patterns of stellar birth and death across galactic scales. The energy injected by supernovas also helps regulate star formation. Without this feedback, gas clouds might collapse too quickly, forming stars at an unsustainable rate. Supernovas inject energy back into the system, heating and stirring the gas, preventing runaway collapse. This balance ensures that galaxies evolve in a controlled and steady manner over time. Inside the remnants of a supernova, conditions remain extreme for thousands of years. Shockwaves continue to travel through the expanding gas, heating it to millions of degrees. Magnetic fields are amplified and twisted, creating complex structures that influence the motion of charged particles. These environments become sources of high-energy radiation and cosmic rays, which propagate throughout the galaxy. Cosmic rays, produced in supernova remnants, are important in shaping the chemistry of interstellar space. They can ionize atoms, trigger chemical reactions, and influence the formation of molecules. These processes play a role in the early stages of star and planet formation, linking supernovas even more deeply to the evolution of cosmic structures. As the remnant expands and cools, it gradually blends into the surrounding interstellar medium. The distinct structure fades, but the material it dispersed remains. Over millions of years, this material becomes part of new clouds, new stars, and new planetary systems. The cycle continues, with each supernova contributing to the ongoing transformation of the galaxy. One of the most important consequences of this cycle is the increasing complexity of matter. Early in the universe, only the simplest elements existed. Through successive generations of stars and supernovas, heavier elements accumulated. This process allowed for the formation of molecules, solids, and eventually the complex chemistry required for life. The connection between supernovas and life is indirect but profound. Without the explosions of massive stars, the elements necessary for biology would not exist in sufficient quantities. Every living organism, every planet, and every complex structure in the universe owes its existence in part to these violent stellar deaths. Even the structure of galaxies is influenced by supernovas over long timescales. The distribution of gas, the rate of star formation, and the chemical composition of stars all reflect the cumulative effect of countless explosions. Galaxies are not static systems. They are constantly evolving, shaped by the life cycles of their stars. In some regions of galaxies, supernova activity is particularly intense. These areas, often associated with massive star formation, experience frequent explosions that drive rapid evolution. In other regions, star formation is slower and supernova activity is less frequent. This creates a diverse range of environments within a single galaxy. As we observe these processes, we begin to see a deeper pattern. The universe is not a collection of isolated events. It is a connected system where the life and death of stars are part of a continuous cycle. Energy flows from one stage to another, matter is recycled, and structures evolve over time. Supernovas are central to this cycle. They mark the transition from one generation of stars to the next. They redistribute matter, drive chemical evolution, and shape the architecture of galaxies. Without them, the universe would be static and chemically limited. With them, it becomes dynamic, diverse, and capable of supporting complexity on every scale. In the vastness of space, every supernova is both an end and a beginning. It is the final moment of a star's life and the first step in the formation of new structures. And through this continuous process, the universe builds itself, one explosion at a time. In the aftermath of a supernova, the universe is not only rearranged in terms of structure and energy, it is fundamentally enriched in a way that changes the very ingredients available for everything that comes after. What was once a simple cosmos made mostly of hydrogen and helium begins to transform into something far more complex. This transformation is driven by one of the most important processes in nature, the creation and distribution of heavy elements inside stars and through their explosive deaths. At the beginning of the universe, shortly after the Big Bang, matter was almost entirely composed of hydrogen and helium. These are the simplest elements, formed when the universe was still hot and dense enough for nuclear reactions to occur on a large scale. There were no planets, no rocky surfaces, no complex chemistry. The universe was chemically simple, even though it was already expanding and cooling. The first generation of stars changed this. As gravity pulled gas together, massive stars formed and ignited nuclear fusion in their cores. Inside these stars, hydrogen was fused into helium, releasing energy and allowing the stars to shine. But fusion did not stop there. In the most massive stars, the process continued, creating progressively heavier elements as the core evolved. Carbon, oxygen, neon, magnesium, silicon, and finally iron were all formed through successive stages of fusion in the interiors of these stars. Each of these elements represents a step in a nuclear ladder, built under extreme temperature and pressure. But this process has limits. The formation of iron marks the end of energy-producing fusion. Beyond iron, fusion no longer releases energy, but instead consumes it. This is why massive stars cannot sustain themselves indefinitely. Once iron accumulates in the core, the star is destined for collapse. When that collapse occurs, it leads to a supernova explosion. This is the moment when the elements forged inside the star are released into space. Until this point, those elements are locked in the core or in surrounding layers, trapped within the structure of the star. The explosion breaks that structure apart, scattering material across vast distances. This scattering is not random. It is a powerful redistribution of matter into the interstellar medium, the vast space between stars. The elements created inside the star are now mixed with existing gas and dust, enriching the environment with heavier atoms. This process fundamentally changes the chemical composition of galaxies over time. Elements heavier than helium are often referred to as metals in astronomical terms. These include everything from carbon and oxygen to iron and gold. Although they make up a small fraction of the total mass of the universe, they are essential for the formation of complex structures. Without them, there would be no rocky planets, no oceans, no atmospheres capable of supporting life as we know it. Supernovas are the primary mechanism by which these heavy elements are spread throughout space. During the explosion, different layers of the star are ejected at different speeds and temperatures. The outer layers, rich in lighter elements, mix with deeper layers that contain heavier elements formed during the star's life. This creates a chemically diverse cloud of material expanding into space. Inside the explosion itself, conditions are so extreme that new elements can also be formed. The shockwave passing through the star triggers rapid nuclear reactions, creating elements heavier than iron. This process, known as rapid neutron capture, or the R process, is responsible for producing some of the rarest and heaviest elements in the universe, including gold, platinum, and uranium. These elements are not produced in large quantities, but their existence depends on the extreme environments created by supernova explosions. Without these events, many of the elements that are essential to planetary systems and technological civilizations would simply not exist. Once these elements are released into space, they do not remain isolated. They become part of the interstellar medium, mixing with gas and dust over time. This enriched material is then recycled into new generations of stars and planetary systems. Each new star contains a slightly higher proportion of heavy elements than the ones before it. This gradual increase in chemical complexity is known as galactic chemical evolution. It is a slow but continuous process that transforms the composition of the universe over billions of years. Early stars were almost entirely composed of hydrogen and helium. Later stars contain a richer mixture of elements, allowing for the formation of planets with solid surfaces and diverse chemistry. The presence of heavy elements also changes the way stars form and evolve. Metal-rich gas cools more efficiently than pure hydrogen and helium, allowing clouds to collapse more easily under gravity. This affects the size, structure, and lifetime of stars that form in these environments. As a result, the universe becomes more diverse, not only chemically, but also structurally. Planets formed in metal-rich environments are fundamentally different from those that could have formed in the early universe. Rocky planets require elements like silicon, iron, and oxygen. These elements come directly from previous generations of stars and their supernova explosions. Without them, there would be no solid surfaces, no mountains, no oceans, and no stable environments for complex chemistry. Even the existence of life depends on this enrichment process. Carbon, the backbone of organic chemistry, is produced inside stars and distributed by supernovas. Oxygen, essential for water, is also created in stellar interiors. Iron, which plays a crucial role in planetary cores and biological systems, is forged in the final stages of massive stars. Every essential element for life is a product of stellar evolution and supernova explosions. In this sense, supernovas are not just destructive events, they are creative forces on a cosmic scale. They take the products of stellar evolution and spread them across galaxies, ensuring that future generations of stars and planets have access to more complex materials. The universe becomes progressively richer in structure and composition over time. The distribution of these elements is not uniform. Supernova remnants expand into the surrounding space, creating regions of enhanced chemical density. These regions can influence the formation of new stars and planetary systems, leading to localized differences in composition within galaxies. Some regions may become enriched more quickly than others, creating a patchwork of chemical environments. Over time, these processes lead to the emergence of galaxies with distinct chemical histories. Some galaxies may experience rapid early enrichment due to frequent supernova activity, while others evolve more slowly. These differences affect everything from star formation rates to the types of planets that can form within them. The cycle of stellar birth, life, and death continues to drive this enrichment process. Each generation of stars contributes to the chemical evolution of the galaxy. Massive stars live short lives, but have a significant impact due to their supernova explosions. Smaller stars live longer and contribute more slowly to the recycling of material. Supernova remnants themselves become important sites of interaction in the interstellar medium. As they expand, they sweep up surrounding gas and dust, compressing it and sometimes triggering new waves of star formation. This creates a feedback loop where star formation leads to supernovas, which in turn trigger more star formation. Inside these expanding remnants, complex physical processes continue to shape the distribution of elements. Shockwaves heat the gas, magnetic fields influence particle motion, and turbulence mixes material from different layers of the explosion. Over time, the remnant becomes less distinct, blending into the surrounding medium but leaving behind a chemically enriched environment. This enrichment is not just important for stars and planets. It also plays a role in the broader structure of galaxies. The distribution of heavy elements affects how gas cools, how stars form, and how galaxies evolve over time. It influences the balance between different phases of interstellar matter, shaping the overall dynamics of the galaxy. Without supernovas, galaxies would remain chemically primitive. They would consist mostly of hydrogen and helium gas, forming simple, long-lived stars with little variation in composition. There would be no rocky planets, no complex chemistry, and no pathway toward biological systems. The universe would be structurally simple and chemically uniform. With supernovas, however, the universe becomes a dynamic system of increasing complexity. Each explosion adds new elements to the cosmic inventory. Each generation of stars builds on the material left behind by previous generations. Over billions of years, this process transforms the universe from a simple gas cloud into a rich and diverse environment capable of supporting complex structures. The atoms that make up everything we see today were once inside stars that lived and died long before the formation of our solar system. The iron in our blood, the calcium in our bones, and the oxygen we breathe all originated in the interiors of massive stars and were distributed across space by supernova explosions. In this way, supernovas connect the life cycles of stars to the existence of planets and life itself. They are the engines of chemical evolution, transforming the universe at the most fundamental level. Through their explosive deaths, stars ensure that the cosmos becomes progressively richer, more diverse, and more capable of supporting complexity. Every element in the periodic table beyond hydrogen and helium carries a history written in the hearts of stars. And every supernova is a chapter in that history, marking the moment when the building blocks of complexity are released into the universe. When a supernova explodes, the most obvious effect is the sudden burst of light that briefly outshines an entire galaxy. But what is far less visible, yet equally important, is the immense wave of energy that spreads outward through space long after the initial flash has faded. This energy does not simply vanish. It travels through the interstellar medium, interacts with gas and dust, compresses vast clouds of matter, and reshapes the structure of entire regions within a galaxy. These are the cosmic shockwaves, invisible architects of galactic evolution. A shockwave in space behaves differently from anything we experience on Earth. There is no air to carry sound, no solid medium to transmit pressure in the usual sense. Instead, a shockwave in space is a propagating disturbance in gas, plasma, and magnetic fields. It is a region where density, temperature, and pressure change abruptly. When a supernova occurs, it injects an enormous amount of energy into its surroundings, forcing this disturbance to expand outward at tremendous speeds. In the first moments after the explosion, the outer layers of the star are ejected at velocities of thousands of kilometers per second. This material collides with the surrounding interstellar gas, creating a powerful forward-moving shock front. Ahead of this front, gas remains relatively undisturbed. Behind it, everything changes. The gas is compressed, heated, and ionized, transforming its physical state in a matter of moments. As this shockwave expands, it sweeps up more and more material from the surrounding environment. The mass of the expanding shell increases over time even as it continues to move outward. This interaction slows the shockwave gradually, but its influence spreads across vast distances, often spanning tens or even hundreds of light years. One of the most important effects of these shockwaves is the compression of interstellar gas clouds. These clouds are the raw material from which new stars are formed. Under normal conditions, many of these clouds are stable, supported by internal pressure, temperature, and magnetic fields that resist gravitational collapse. But when a supernova shockwave passes through, it disrupts this balance. The compression caused by the shockwave increases the density of certain regions within the cloud. As density rises, gravity becomes more effective at pulling material inward. Small fluctuations in density are amplified, leading to the formation of dense cores within the cloud. These cores eventually collapse under their own gravity, giving birth to new stars. This process is known as triggered star formation. It is one of the key ways in which supernovas influence the evolution of galaxies. Rather than simply destroying matter, they actively reorganize it, setting the stage for new cycles of stellar birth. The regions where this compression occurs are often not uniform. Instead, the shockwave interacts with the cloud in complex ways, shaped by the cloud's structure, density variations, and magnetic fields. Some areas may be compressed strongly, while others are barely affected. This leads to a patchwork of star-forming regions, each evolving at its own pace. Inside these compressed regions, the process of collapse begins slowly at first. Gas gathers into denser clumps, cooling as it contracts. Over time, these clumps become more and more compact, eventually forming protostars. As these protostars grow, they heat up, and nuclear fusion eventually ignites in their cores, marking the birth of new stars. This chain reaction, initiated by a single supernova, can lead to the formation of entire clusters of stars. In some cases, a supernova can trigger star formation across multiple regions of a galaxy, influencing structures on a truly massive scale. But shockwaves do more than just compress gas. They also heat and ionize it. As the shock front passes through the interstellar medium, it raises temperatures to millions of degrees. At these temperatures, atoms are stripped of their electrons, creating a plasma state where charged particles move freely. This ionized gas emits radiation across a wide range of wavelengths, including visible light, X-rays, and radio waves. These emissions allow astronomers to observe supernova remnants long after the initial explosion. Even when the visible light of the supernova has faded, the expanding shockwave continues to glow as it interacts with the surrounding medium. These glowing structures are some of the most striking features in the galaxy, revealing the long-term impact of stellar explosions. The interaction between shockwaves and the interstellar medium is also influenced by magnetic fields. Space is not empty of magnetism. Galaxies are threaded with large-scale magnetic fields that influence the motion of charged particles. When a shockwave passes through these fields, it can distort and amplify them, creating complex patterns of turbulence. This turbulence plays an important role in mixing material within the galaxy. It helps distribute heavy elements produced in the supernova more evenly, ensuring that future generations of stars form from enriched material. It also influences the structure of gas clouds, shaping them into filaments, sheets, and clumps that serve as the sites of future star formation. Another important consequence of shockwaves is the acceleration of cosmic rays. As charged particles encounter the moving shock front, they can be accelerated to extremely high energies through repeated interactions. This process, known as diffusive shock acceleration, turns supernova remnants into powerful natural particle accelerators. Cosmic rays produced in this way travel through the galaxy, carrying energy and influencing chemical processes in interstellar space. When they interact with gas clouds, they can ionize atoms and molecules, triggering chemical reactions that would otherwise not occur. This contributes to the complex chemistry observed in molecular clouds, where new stars and planets are forming. Over time, the shockwave continues to expand and weaken. As it travels farther from the original explosion, it sweeps up more material and loses energy. Eventually, it slows down to the point where it can no longer be distinguished as a distinct structure. At this stage, it merges with the surrounding interstellar medium, leaving behind a region of enriched and disturbed gas. Even though the shockwave fades, its effects persist. The regions it has passed through are permanently altered. Gas has been compressed, stars have been formed, and elements have been redistributed. The structure of the galaxy has been subtly reshaped by a single event that may have lasted only a few seconds at its peak. In many cases, multiple supernovae occur within the same region over time. This can lead to the formation of large cavities in the interstellar medium known as superbubbles. These structures are carved out by successive shockwaves, creating vast regions of low-density gas surrounded by dense shells of material. Within these shells, star formation can be particularly active, driven by repeated compression events. Superbubbles are a clear example of how supernovas work together to influence galactic structure on large scales. Rather than being isolated events, they contribute to a collective process that shapes the distribution of matter across entire regions of a galaxy. The study of shockwaves also reveals the dynamic nature of galaxies. Far from being static collections of stars, galaxies are constantly evolving systems where energy flows through multiple channels. Supernova shockwaves are one of the most important drivers of this evolution, transferring energy from individual stars into the larger galactic environment. These processes also help regulate the rate of star formation. Without feedback from supernova shockwaves, gas clouds might collapse too quickly, leading to bursts of star formation that exhaust available material. Shockwaves inject energy back into the system, preventing runaway collapse and maintaining a balance between star formation and gas dispersion. This regulatory role is essential for the long-term stability of galaxies. It ensures that star formation occurs over extended periods, allowing galaxies to evolve gradually rather than collapsing into rapid, short-lived bursts of activity. As we observe galaxies across the universe, we see clear evidence of these processes at work. Regions of active star formation are often associated with supernova remnants and shockwave structures. Filaments of gas trace the paths of past explosions, while clusters of young stars mark the sites of triggered collapse. In this way, the life and death of stars are deeply interconnected. The death of one star can lead directly to the birth of many others. Shockwaves act as the bridge between these two phases, carrying energy and matter from one generation to the next. Over cosmic timescales, this cycle repeats countless times. Each supernova adds new layers of complexity to the galaxy. Each shockwave reshapes the environment in subtle but significant ways. And through this continuous process, galaxies evolve from simple gas clouds into rich, structured systems filled with stars, planets, and the ingredients for life. In the end, cosmic shockwaves are not just remnants of stellar explosions. They are active participants in the ongoing story of the universe. They connect death to creation, destruction to formation, and chaos to structure. Through them, the universe continually rebuilds itself, guided by the energy released in the final moments of dying stars. The universe does not treat destruction as an ending. Instead, it treats it as a transformation. When a massive star explodes as a supernova, it does not simply disappear from existence. Its material is scattered, its energy is released, and its influence spreads far beyond the site of the explosion. In the aftermath of this violent event, something remarkable begins to happen. The debris left behind does not remain chaotic forever. Over time, it becomes the foundation for new structures, new systems, and new worlds. From the remnants of stellar death, the birth of new stars and planets begins. After a supernova shockwave has passed through a region of space, the interstellar medium is left in a very different state. Gas clouds that were once stable may now be compressed, heated, and chemically enriched. These clouds are no longer uniform. They contain regions of varying density, temperature, and composition. Some areas are disturbed and turbulent, while others begin to settle into new forms of balance. This is the environment in which new stars are born. Gravity plays the central role in this transformation. Once a region of gas becomes dense enough, gravity begins to dominate all other forces. It pulls material inward, causing the cloud to collapse. This collapse is not instantaneous. It unfolds over thousands or even millions of years. But once it begins, it is difficult to stop. The cloud fragments into smaller and smaller pieces, each one becoming a potential star. Inside these collapsing regions, temperature and pressure rise steadily. As the material contracts, gravitational energy is converted into heat. The core of each fragment becomes hotter and denser over time. Eventually, when conditions become extreme enough, nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, releasing energy that halts the collapse. At this moment, a new star is born. But star formation is only part of the story. Surrounding each newborn star is a rotating disk of gas and dust. This disk forms naturally as the collapsing cloud conserves angular momentum. As material falls inward, any slight rotation becomes amplified, flattening the material into a spinning structure. This protoplanetary disk becomes the birthplace of planets. Within this disk, particles of dust collide and stick together. Over time, these small grains grow into larger and larger bodies. The process is gradual but persistent. Tiny particles become pebbles, pebbles become rocks, and rocks become planetesimals. Through continued collisions and gravitational attraction, these bodies merge into protoplanets. The composition of these forming planets depends heavily on the material present in the disk. Because supernovas have enriched the interstellar medium with heavy elements, the disks that form after them contain a diverse mixture of chemical building blocks. Silicates, metals, carbon compounds, and ices all play a role in planetary formation. This chemical diversity is essential for the creation of complex planetary systems. Closer to the newborn star, temperatures are too high for volatile compounds like water and methane to condense. In these inner regions, only metals and silicates can remain solid. This leads to the formation of rocky planets. Farther out, where temperatures are lower, volatile compounds can freeze allowing the formation of icy bodies and gas giants. This natural sorting process creates structured planetary systems with distinct regions. The early stages of planetary formation are chaotic. Collisions between growing bodies are frequent and often violent. Some protoplanets are destroyed and reabsorbed into the disk, while others merge into larger structures. Over time, however, the system begins to stabilize. A few dominant planets emerge, clearing their orbits and shaping the structure of the system. This entire process is deeply connected to the supernova that preceded it. Without the heavy elements produced in earlier stars and distributed by their explosive deaths, rocky planets would not exist. Without the shockwaves that compress gas clouds, star formation would be much rarer and less efficient. Every stage of this cycle depends on the energy and material released by dying stars. As planets form, they begin to differentiate internally. Heavier elements sink toward their centers, forming metallic cores, while lighter materials form mantles and crusts. This internal structure is crucial for long-term planetary stability. It also plays a role in generating magnetic fields, which can protect planetary atmospheres from stellar radiation. In some cases, conditions on newly formed planets may become suitable for the emergence of complex chemistry. Liquid water, organic molecules, and stable energy sources can combine to create environments where chemical evolution becomes possible. While the details of how life arises remain one of the deepest mysteries in science, it is clear that the ingredients necessary for it are directly linked to the life cycles of stars. Supernovas are therefore not just creators of stars and planets, they are also indirect creators of the conditions that allow complexity to emerge. By producing and distributing the elements needed for chemistry, they set the stage for everything from planetary geology to biological systems. As time progresses, planetary systems continue to evolve. Orbits stabilize, atmospheres develop, and geological processes reshape surfaces. But the memory of their origin remains embedded in their composition. The elements that make up these worlds carry the signature of ancient stellar explosions. Even the structure of galaxies reflects this ongoing cycle. Regions of active star formation are often located near areas enriched by previous supernovas. Waves of starbirth propagate through galaxies, driven by successive generations of stellar death and rebirth. This creates a dynamic, ever-changing environment on galactic scales. In some regions, star formation occurs in clusters, producing groups of stars that share a common origin. These clusters may contain stars of varying masses, each following its own evolutionary path. Massive stars within the cluster evolve quickly, ending their lives as supernovas and influencing the environment of the surrounding region. Lower mass stars continue to shine for much longer periods, providing stability to the system. Over time, these clusters may disperse, with individual stars drifting apart due to gravitational interactions. Yet, even as they separate, they carry with them the chemical and structural imprint of their shared origin. Each star becomes part of the larger galactic ecosystem, contributing to the ongoing cycle of matter and energy. The birth of new stars and planets is not a rare or isolated event. It is a continuous process occurring throughout galaxies. Everywhere that gas clouds exist, the potential for collapse and formation is present. And everywhere that supernovas have enriched the environment, the ingredients for complex systems are available. This cycle of destruction and creation is one of the fundamental patterns of the universe. Stars are born from collapsing gas clouds. They live out their lives by fusing elements in their cores, and they eventually die in explosive events that return their material to space. From this recycled matter, new stars and planets emerge, continuing the cycle. In this sense, nothing in the universe is truly final. Even the most violent destruction leads to new beginnings. The death of a star is not an endpoint, but a transition into a different phase of cosmic evolution. As we observe distant regions of space, we see this cycle playing out on vast scales. Nebulae glowing with the light of young stars, dark clouds collapsing under gravity, expanding shells of gas marking the remnants of ancient supernovas. Each of these structures represents a different stage in the same continuous process. The universe, when viewed in this way, is not static. It is a system in constant transformation. Matter flows from one form to another. Energy is transferred, redistributed, and reused. Structures form, evolve, and dissolve, only to give rise to new structures again. The formation of new stars and planets from supernova remnants is one of the most important mechanisms driving this cosmic evolution. It ensures that the universe becomes increasingly complex over time. It allows for the emergence of diverse planetary systems and creates the conditions necessary for chemical and potentially biological complexity. Every atom in a planet, every molecule in an atmosphere, and every element in a living system can trace its origin back to stars that lived and died long before the current generation of cosmic structures. In this way, the universe is deeply interconnected across time. The past is not gone. It is embedded in the present. And so, from the violent death of stars comes the quiet formation of new worlds. From shockwaves that once tore through space come the calm environments where planets take shape. And from the scattered remnants of ancient explosions, the universe builds itself again and again in an endless cycle of destruction and creation. Galaxies are not static collections of stars. They are living systems in the sense that they evolve, respond, and restructure themselves over vast periods of time. Within these enormous structures, supernovas act as both disruptors and builders. They destroy individual stars, but in doing so, they influence the behavior of entire galaxies. Their impact is not limited to a single point in space. It spreads through gas, dust, radiation, and shockwaves, shaping the very architecture of galactic evolution. To understand how supernovas influence galaxies, we first need to understand what a galaxy actually is at its core. A galaxy is a gravitationally bound system composed of stars, interstellar gas, dust, dark matter, and remnants of past stellar evolution. These components are not evenly distributed. Instead, they form complex structures such as spiral arms, central bulges, and diffuse halos. Within these structures, matter is constantly in motion, influenced by gravity, radiation pressure, magnetic fields, and stellar feedback. Supernovas are one of the most powerful forms of stellar feedback. When a massive star explodes, it releases enormous amounts of energy into the surrounding environment. This energy does not remain localized. It propagates outward, interacting with interstellar gas and influencing the conditions for future star formation. Over time, the cumulative effect of many supernovas shapes the structure and behavior of the entire galaxy. One of the most important roles of supernovas in galaxies is regulating star formation. Star formation is a process that depends on the collapse of cold, dense gas clouds under gravity. If nothing interfered with this process, large regions of a galaxy could collapse rapidly, forming stars at an unsustainable rate. However, supernovas inject energy back into the interstellar medium, heating and stirring the gas and preventing it from collapsing too quickly. This feedback mechanism creates a balance between star formation and stellar destruction. When star formation becomes too intense in a region, more massive stars are produced. These massive stars live short lives and end in supernova explosions. The energy from these explosions then disrupts nearby gas clouds, slowing down or even temporarily halting further star formation. Over time, the gas cools again, and the cycle restarts. This self-regulating system ensures that galaxies evolve in a controlled and sustained manner, rather than collapsing into short bursts of activity. The distribution of supernovas within a galaxy is not random. They tend to occur in regions where massive stars form, which are often located in spiral arms of disk galaxies. These spiral arms are not rigid structures. They are density waves, regions where gas is compressed as it orbits the galactic center. This compression triggers star formation, leading to the birth of massive stars that will eventually become supernovas. As these stars explode, they reinforce and modify the structure of the spiral arms. Shockwaves from supernovas can compress nearby gas, triggering new waves of star formation along the arms. At the same time, they can also disperse gas, creating gaps and irregularities. This creates a dynamic interplay between formation and destruction that maintains the spiral structure over time. In addition to shaping star formation, supernovas also play a crucial role in distributing chemical elements throughout galaxies. As we have seen, heavy elements are produced inside stars and released during supernova explosions. These elements mix with the interstellar medium, gradually enriching it over time. This enrichment is not uniform. Regions with higher rates of star formation and supernova activity tend to become more chemically enriched than quieter regions. This uneven distribution of elements affects the types of stars and planets that form in different parts of a galaxy. Metal-rich regions are more likely to form rocky planets and complex chemical systems, while metal-poor regions may produce simpler stellar and planetary structures. Over time, this leads to chemical diversity within galaxies, with different regions evolving along slightly different paths. Supernovas also contribute to the heating and ionization of the interstellar medium. The energy they release creates hot bubbles of gas that expand into surrounding cooler regions. These bubbles can merge to form large cavities known as superbubbles. Superbubbles are regions of low density surrounded by dense shells of gas. Within these shells, conditions are often favorable for star formation, as the compressed gas can collapse under gravity. In this way, supernovas not only suppress star formation in some regions, but also trigger it in others. They create a complex pattern of suppression and stimulation that shapes the overall distribution of stars in a galaxy. This interplay helps explain why galaxies have such varied and structured appearances. The influence of supernovas extends beyond gas and stars. They also affect the dynamics of cosmic rays, which are high-energy particles that travel through space at nearly the speed of light. Supernova remnants are one of the primary sources of these particles. As shockwaves propagate through space, they accelerate charged particles through repeated interactions, giving them enormous amounts of energy. These cosmic rays then travel throughout the galaxy, interacting with magnetic fields and interstellar matter. They can ionize atoms, influence chemical reactions, and contribute to the overall energy balance of the interstellar medium. In this way, supernovas indirectly affect processes far beyond their immediate surroundings. On larger scales, the cumulative effect of many supernovas can influence the overall evolution of a galaxy. In galaxies with high rates of star formation, such as starburst galaxies, supernova activity can become extremely intense. The combined energy from many overlapping explosions can drive powerful galactic winds. These winds push gas out of the galaxy, reducing the material available for future star formation. This process can significantly alter the evolution of a galaxy. By removing gas, supernova-driven winds can slow down or even shut off star formation in certain regions. This leads to changes in the structure, brightness, and long-term development of the galaxy. In contrast, galaxies with lower rates of star formation experience fewer supernovas and therefore less energetic feedback. In these systems, gas can remain in place for longer periods, allowing star formation to proceed more gradually. This leads to different evolutionary paths for different types of galaxies. The balance between gas inflow, star formation, and supernova feedback is one of the key factors that determines the life cycle of galaxies. Gas flows into galaxies from intergalactic space. Star formation converts that gas into stars, and supernovas return energy and material back into the interstellar medium. This continuous cycle regulates the growth and evolution of galaxies over billions of years. Supernovas also influence the distribution of dark matter indirectly. While dark matter does not interact with light or ordinary matter in the same way, its gravitational presence shapes the overall structure of galaxies. The redistribution of gas and stars caused by supernova feedback can alter the gravitational potential of a galaxy, which in turn affects how dark matter is distributed on large scales. Over time, these processes contribute to the diversity of galaxy types observed in the universe. Some galaxies become large, structured spirals with ongoing star formation. Others evolve into elliptical galaxies with older stellar populations and little new star formation. Supernovas play a key role in determining which path a galaxy follows. Even the intergalactic medium, the vast space between galaxies, is influenced by supernovas. In some cases, energetic outflows driven by supernova activity can expel gas beyond the boundaries of a galaxy. This material enriches the intergalactic medium with heavy elements, spreading the products of stellar evolution across the universe on the largest scales. This means that supernovas do not only shape individual galaxies, they contribute to the chemical and energetic evolution of the universe as a whole. Every explosion sends ripples of matter and energy outward, connecting galaxies through shared processes of enrichment and feedback. When we observe distant galaxies, we are seeing the combined effect of billions of years of this activity. The shapes, colors, and compositions of galaxies all carry the imprint of countless supernova explosions. They are not random structures, but the result of long-term cosmic evolution, driven in part by the life cycles of stars. In the end, supernovas are not just endpoints in stellar evolution, they are essential mechanisms in the evolution of galaxies. They regulate star formation, distribute elements, drive energetic feedback, and shape large-scale structure. Without them, galaxies would be simpler, less dynamic, and chemically less diverse. Through their explosive deaths, stars help define the character of the galaxies they inhabit. And through this process, they ensure that the universe remains a place of continuous transformation, where structure is constantly being built, destroyed, and rebuilt again across cosmic time. When a massive star reaches the end of its life and collapses under its own gravity, the outcome is not always the same. Some collapses lead to neutron stars, incredibly dense remnants where matter is packed to the limits allowed by quantum mechanics. Others go even further, where gravity overwhelms every known form of resistance, creating one of the most extreme objects in the universe, a black hole. In both cases, the original star is gone, but what remains continues to shape space, time, and the evolution of the cosmos in profound ways. To understand these remnants, we must return to the moment of core collapse. Inside a massive star, nuclear fusion builds elements layer by layer until iron forms at the center. Iron cannot produce energy through fusion, so the core loses its support system. Gravity takes over completely. In a fraction of a second, the core collapses inward at an extraordinary speed, compressing matter to densities far beyond ordinary experience. If the mass of the collapsing core is below a certain threshold, something remarkable happens. The collapse is halted by neutron degeneracy pressure, a quantum mechanical effect that arises because neutrons cannot occupy the same state in the same space. At these extreme densities, this resistance becomes powerful enough to stop further collapse. The result is a neutron star. A neutron star is one of the most extreme objects in the universe. It typically has a diameter of only about 20 kilometers, yet it contains more mass than the Sun. This means that a single teaspoon of neutron star material would weigh billions of tons on Earth. The density is so extreme that atomic structure no longer exists in any familiar form. Electrons have been forced into protons, forming a sea of neutrons packed tightly together. Despite their small size, neutron stars have powerful effects on their surroundings. Many of them rotate extremely rapidly, sometimes hundreds of times per second. As they spin, they can emit beams of radiation from their magnetic poles. If these beams sweep across Earth, we observe them as pulses of radiation, which is why some neutron stars are known as pulsars. These pulsars act like cosmic lighthouses, sending regular signals across space. Their precise timing makes them some of the most accurate natural clocks in the universe. By studying them, astronomers can test the laws of physics under conditions that cannot be reproduced on Earth. Neutron stars also possess incredibly strong magnetic fields, often trillions of times stronger than Earth's magnetic field. These fields can accelerate particles to extreme energies, creating regions of intense radiation around the star. In some cases, magnetic activity can produce sudden bursts of energy known as magnetar flares, which are among the most powerful events in the galaxy. But not all stellar collapses stop at the neutron star stage. If the core of the collapsing star is too massive, even neutron degeneracy pressure cannot withstand gravity. In this case, the collapse continues without limit. Matter is compressed beyond the point where known physics can describe it. The result is a black hole. A black hole is not an object in the traditional sense. It is a region of space where gravity is so strong that nothing, not even light, can escape. At its center lies a point of infinite density, known as a singularity, surrounded by an event horizon. The event horizon is the boundary beyond which escape becomes impossible. Once anything crosses this boundary, it is permanently trapped. The formation of a black hole marks the final stage in the life of a massive star. Unlike neutron stars, black holes do not emit light or radiation directly from their surface. They are invisible in the traditional sense. We detect them indirectly through their gravitational effects on nearby matter. Gas falling into a black hole heats up and emits radiation before crossing the event horizon, creating bright accretion disks that can be observed across vast distances. Black holes challenge our understanding of space and time in fundamental ways. Near the event horizon, the curvature of space-time becomes extreme. Time slows down relative to distant observers. Light is bent and distorted. The closer one gets to the event horizon, the more dramatically these effects increase. In this region, the familiar rules of physics begin to break down. Inside the event horizon, our current theories cannot fully describe what happens. General relativity predicts a singularity, a point where density becomes infinite and space-time curvature becomes undefined. This signals the breakdown of known physics and suggests that a deeper theory is needed to understand what truly occurs in these extreme conditions. Despite being invisible, black holes play a major role in shaping galaxies. Many galaxies contain supermassive black holes at their centers, with masses millions or even billions of times that of the Sun. These giants influence the motion of stars and gas in their surrounding regions, acting as gravitational anchors around which entire galaxies rotate. The interaction between black holes and surrounding matter can also produce some of the most energetic phenomena in the universe. As gas falls toward a black hole, it forms a rapidly spinning accretion disk. Friction and gravitational forces heat this material to extreme temperatures, causing it to emit intense radiation, sometimes outshining entire galaxies. In some cases, powerful jets of particles are launched from the regions near black holes, traveling vast distances through space. These jets are believed to be driven by complex interactions between magnetic fields and rotating space-time. They can extend far beyond the host galaxy, injecting energy into the intergalactic medium and influencing the evolution of surrounding structures. Neutron stars and black holes represent two different outcomes of stellar collapse, but both are essential to understanding the life cycle of matter in the universe. They are the final states of massive stars, yet they are also active participants in cosmic evolution. Through their gravity, radiation, and energetic processes, they continue to shape their surroundings long after their formation. In some cases, neutron stars can merge with other neutron stars or black holes. These collisions release enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. The detection of these waves has opened a new window into the universe, allowing scientists to observe events that were previously invisible. Black holes can also merge with each other, forming larger and more massive black holes. These mergers release bursts of gravitational energy that propagate across the universe. Each event carries information about the nature of gravity, space-time, and the extreme conditions under which these objects exist. The existence of neutron stars and black holes demonstrates that the end of a star is not a simple disappearance. Instead, it is a transformation into some of the most exotic states of matter and space-time known to science. These remnants are not passive. They are active, evolving objects that continue to influence the universe on multiple scales. They also serve as laboratories for testing fundamental physics. The extreme densities, magnetic fields, and gravitational forces present in neutron stars and black holes push physical laws to their limits. By studying them, scientists can explore conditions that are impossible to replicate on Earth. In a broader sense, these objects remind us that the universe is not static. It is filled with processes that operate across unimaginable scales of energy and time. Stars are born, they evolve, and they die. But their remnants continue to shape the structure of galaxies and the flow of matter and energy across the cosmos. Neutron stars and black holes are the final chapters in the lives of massive stars, but they are also new beginnings in the ongoing story of the universe. Through them, gravity reveals its most extreme behavior, matter reaches its ultimate limits, and space-time itself becomes a dynamic, active participant in cosmic evolution. And so, even in the darkness left behind by dying stars, the universe continues to write its story, shaped by remnants that are as powerful as they are mysterious. The universe is not defined by a single moment, event, or structure. It is defined by change. Every process we observe, from the smallest atomic interaction to the largest galactic evolution, is part of a continuous transformation that has been unfolding for billions of years. Supernovas, black holes, neutron stars, star formation, and galaxy evolution are not separate stories. They are chapters in a single, ongoing process where energy and matter are constantly being reshaped. At the center of this process lies a deeper question about time itself and the nature of the universe as a whole. Time is often perceived as a steady, unchanging flow. In everyday life, it feels absolute, moving forward at a constant rate. But in the universe, time is not uniform. It is deeply connected to gravity, motion, and energy. According to our best understanding of physics, time can stretch, slow down, and even behave differently depending on conditions in space. Near massive objects like black holes, time moves more slowly compared to regions farther away. This means that time itself is part of the structure of the universe, not something separate from it. Space and time together form a single framework known as space-time. This framework is dynamic. It can curve, stretch, and warp depending on the distribution of mass and energy. Stars, planets, galaxies, and black holes all influence the shape of space-time. In return, the shape of space-time determines how these objects move and evolve. This relationship is one of the most fundamental aspects of the universe. Supernovas are powerful examples of how energy can reshape space-time. When a massive star explodes, it releases an enormous amount of energy in a short period of time. This energy does not just move through space. It interacts with space-time itself, creating waves of distortion known as gravitational waves. These waves travel outward at the speed of light, carrying information about the most violent events in the universe. Gravitational waves were first predicted as a consequence of Einstein's theory of general relativity. For a long time, they remained purely theoretical. But in recent years, they have been directly detected, confirming that space-time is not rigid. It is flexible and dynamic, capable of transmitting energy across vast cosmic distances. Events like supernova explosions, neutron star collisions, and black hole mergers all contribute to this background of gravitational activity. These ripples in space-time provide a new way of observing the universe. Unlike light, which can be absorbed or scattered by matter, gravitational waves pass through everything almost without obstruction. They carry information directly from the most extreme environments in the cosmos, allowing scientists to study events that would otherwise be invisible. As we zoom out from individual events, we begin to see the universe as a connected system. Stars are born from collapsing gas clouds. They evolve through nuclear fusion. They end their lives in supernova explosions or collapse into neutron stars and black holes. Their remnants are recycled into new generations of stars and planets. This cycle repeats continuously across billions of years. This cycle is not random. It follows physical laws that govern the behavior of matter and energy. Gravity pulls material together, forming structures. Nuclear fusion powers stars, allowing them to shine and evolve. Explosive events like supernovas redistribute matter and energy, preventing systems from becoming static. Over time, these processes lead to increasing complexity in the universe. One of the most important outcomes of this cycle is chemical evolution. Early in the universe, only the simplest elements existed. Hydrogen and helium made up nearly all matter. But through the life cycles of stars and their explosive deaths, heavier elements were created and distributed. Carbon, oxygen, nitrogen, silicon, iron, and many others were formed inside stars and released into space through supernovas. These elements are the foundation of complexity. They allow for the formation of rocky planets, atmospheres, oceans, and eventually the chemistry necessary for life. Without the repeated cycle of stellar birth and death, the universe would remain chemically simple and structurally uniform. There would be no diversity of planets, no complex molecules, and no pathway toward biological systems. As galaxies evolve, they reflect this increasing complexity. Spiral galaxies like our own Milky Way show structured arms filled with regions of active star formation. Elliptical galaxies contain older stars and less gas, representing a different stage of evolution. Irregular galaxies show chaotic structures shaped by interactions and past explosions. Each galaxy carries the imprint of countless supernova events that have shaped its history. On the largest scales, the universe itself is structured like a vast network. Galaxies are connected by filaments of gas and dark matter, forming a cosmic web. Between these filaments are vast voids where matter is sparse. Supernovas contribute to this structure by regulating star formation and distributing energy throughout galaxies, influencing how matter flows across cosmic scales. Even black holes, which represent the final stage of stellar collapse, are not isolated endpoints. They interact with their surroundings through gravity and energy emission. Supermassive black holes at the centers of galaxies influence the motion of stars and gas, shaping the evolution of entire galactic systems. When they accrete matter, they release enormous amounts of energy that can affect star formation across large regions. In this way, every stage of stellar evolution is connected. From the formation of a star in a gas cloud to its death in a supernova or collapse into a black hole, each phase contributes to the larger structure of the universe. Nothing exists in isolation. Everything is part of a continuous flow of matter and energy. Time itself is the thread that connects these processes. But unlike a simple linear progression, cosmic time is layered and complex. Different regions of the universe evolve at different rates. Massive stars live short, intense lives, while small stars can burn for trillions of years. Galaxies evolve over billions of years, while individual events like supernovas occur in seconds. These different timescales coexist within the same universe. This creates a layered history of the cosmos. At any given moment, the universe contains objects at every stage of evolution. New stars are forming, mature stars are shining, and old stars are dying. Black holes are growing, galaxies are merging, and gas is flowing through interstellar space. The universe is never in a final state. It is always in transition. Even the concept of an ending becomes unclear on cosmic scales. A supernova marks the end of a star, but it also marks the beginning of new processes. The material it releases becomes part of new stars and planets. A black hole may seem like a final state, but it continues to interact with its environment through gravity and radiation. There is no absolute endpoint, only transformation. This perspective changes how we understand existence itself. Rather than being a collection of separate objects, the universe becomes a single evolving system. Every event is connected to previous events and influences future ones. The death of a star billions of years ago can lead to the formation of a planet which may eventually develop conditions for life. In this sense, supernovas are not just astronomical phenomena, they are key moments in a much larger story. They mark transitions between different states of matter, energy, and structure. They drive the evolution of galaxies and enable the formation of complex systems. Without them, the universe would be fundamentally different. As we look deeper into space, we are also looking back in time. Light from distant galaxies has traveled for billions of years before reaching us. When we observe supernovas in distant galaxies, we are seeing events that occurred long before our own solar system formed. This means that the universe we observe is also a record of its own history. Every supernova we detect is a message from the past. It tells us about the life and death of stars in distant regions of space and long ago in time. It reveals how elements were distributed, how galaxies evolved, and how structures formed on cosmic scales. In the end, the study of supernovas is not just about understanding explosions. It is about understanding the universe as a whole. It is about seeing how matter and energy flow through space and time, how structures form and dissolve, and how complexity emerges from simplicity. The universe is not static, it is a process, and within that process, supernovas are some of the most powerful forces of change. They destroy, but they also create. They end individual stellar lives, but they make possible the next generation of stars, planets, and potentially life itself. And so the story continues, not as a closed system, but as an ongoing expansion of structure, energy, and time. A universe in motion, always changing, always evolving, and always building itself anew from the remnants of what came before.